Today, we will exploring the science behind one of the most demanding and powerful swimming techniques, the butterfly stroke. So, what is butterfly stroke? The butterfly stroke is a visually stunning but physically exhausting swimming style that requires simultaneous arm moves and a synchronized dolphin kick. Although the movement appears fluid, a successful stroke depends on core strength, precise timing, joint mobility, and explosive muscle activation. By understanding the biomechanics and kinesiology involved, we can see how the body works together to produce maximum propulsion and efficiency in the water. In this video, we will discuss the importance of biomechanics, the purpose of the stroke, the movement phase, and the muscle action that involve.
Now, for the importance of biomechanics in butterfly stroke swimming. Because both arms recover out of water simultaneously, it is arguably the most physically demanding stroke in swimming, characterized by massive fluctuation in forward velocity. To overcome this, elite swimmers rely on precise mechanics. Today, we will focus on two critical principles: coordination and undulation. First is spatial temporal coordination, specifically the 2-to-1 arm-to-leg coupling. To maintain a steady forward velocity, a swimmer must execute exactly 2 downward dolphin kicks per single arm cycle. The first kick happens precisely during hand entry and catch phase. This keeps the hips high and eliminates any dead glide time. The second kick occurs during the leg push phase, providing a powerful vertical lift needed to clear the arms over the surface during recovery. The second key principle is full body undulation and active drag mitigation. Butterfly is a short axis stroke. Momentum is generated as a continuous body wave, passing sequentially from the head through the trunk and down to the feet. The biomechanical goal here is maintaining center of mass control. Skilled swimmers keep their body weight flat and close to the surface. If a swimmer undulates too deeply or lifts their chest too high to breathe, their frontal surface area increases. This causes a massive spike in active hydrodynamic drag, which quickly exhausts the athlete.
Okay, now let's see for the purpose of the movement. Before I start, let me introduce 5 phases in the butterfly stroke. First, we have entry phase, catch phase, pull phase, push phase, and recovery phase. Okay, for the purpose of the movement, first, maximizing propulsive force. The main purpose of identifying the pull phase and the push phase is to optimize the generation of forward speed. In the butterfly stroke, the push phase serves as the strongest propulsive driver. Biomechanical analysis helps swimmers understand exactly when and how to accelerate their hand backward past the hip to achieve maximum velocity. Okay. Second, reducing active hydrodynamic drag. As a detail in the entry phase, maintaining a streamlined body and keeping the head facing downward is essential. The purpose of emphasizing this mechanism is to minimize frontal resistance as the swimmer pierces the water. Ensure that the momentum gained from the previous stroke is not lost. Okay, next, improving stroke efficiency and energy conservation. The recovery phase explicitly note that the arm should move above the water in a relaxed but controlled manner. Making this phase out reminds swimmers to conserve energy and rest the shoulder muscle briefly during the airborne phase, preventing premature fatigue while longer rests. Okay, for the next, establish early water traction, which is the catch phase. Okay, the catch phase is dedicated entirely to pressing the hand outward or downward to grip the water while keeping the elbow high. The purpose of focusing on this specific phase is to establish a solid anchor point in the water before applying maximum power, preventing the hands from slipping uselessly in the water column. Okay, and the last one is synchronizing the arm stroke with the breathing and kicking rhythm. The butterfly stroke relies heavily on perfect timing between the upper and lower body, as noted in the entry phase, which is coinciding with the dolphin kick, and the pull phase, which is coinciding with inhalation. Isolating this step help coaches and athlete sync the breathing pattern and the two distinct dolphin kicks per arm cycle perfectly. That's all.
The next is a movement and phase for the butterfly stroke. First phase is entry phase. The arm into the water in front of the shoulder with the elbow slightly bent. At the same time, body remains streamlined and the head face downward. The leg begin in a dolphin kick to maintain body position and forward movement. For the second phase is a catch phase. During this phase, the swimmer press the head outward and downward to grip the water. The elbows stay high to prepare for the strong pull. For the third phase is a pull phase. The swimmer pulls the arm under the body in a semicircular motion. This phase creates a main forward propulsion. The swimmer usually inhale during this movement. The next is a push phase. The hand push backward past of the hip to complete underwater stroke. This is a strong propulsion phase. Lastly, recovery phase. The arm recover above the water and the relax, but control movement. The body underlies smooth with the prepare for the next stroke circle.
The butterfly stroke recruits muscles across the entire body, organized into three key phases: the early pull, late pull, and recovery. For the first one, early pull, as the hand enter the water and begin the catch. The bicep brachii contract concentrically to flex the elbow, while the latissimus dorsi and pectoralis major both contract concentrically to drive the shoulder extension and adduction. Supporting all of this, the internal oblique, external oblique, and rectus abdominis engage isometrically, stabilizing the trunk and maintaining the body wave-like inclination. For the phase 2, leg pull, as the pull continues through the water, the tricep brachii concentrically extend the elbow to complete the push, while the latissimus dorsi continue its concentric shoulder extension. The lower trapezius concentrically depress the scapula, a key movement for protecting the shoulder joint. Meanwhile, a rectus femoris contract concentrically to drive hip flexion in the dolphin kick, and the core oblique continue their isometric stabilization role. Lastly, for the phase 3 recovery, as the arm swing forward out of the water, the tricep brachii concentrically extend the elbow, the striatus anterior protract the scapula, and the upper and lower trapezius work together to elevate then depress the scapula in a controlled arc. Through the entire stroke, the rectus spinae contract isometrically to maintain spinal stabilization.